Okay, so good afternoon. So today we're going to start looking at image transform. And so we're going to start with the Z transform. Just look at the extension from the 1D case you've seen last year. And we're going to see how it extends to 2D. We're going to move on as well to the Fourier transform. That probably will be later on this week. So in the next few weeks, in the next few handouts, really it's all about transforms. And we see the Fourier transform, we see the DCT, we see the Haar transform, and we'll finish with all wavelet transforms. And the reason why we are going to look so much at transforms is because, and something we're going to see in more details afterwards, so when you do compression, you're going to see that you can't really use images as you would do with text, for instance, okay? So just looking at the value of the pixel by itself is not very useful, okay? So what we need to have is a better representation. And the trick that you do in image, but it's true as well of audio processing, is first to transform your signal into a domain where things are a bit more compact and easier to compress, okay? So the first stage really of most of these compression algorithms is to transform your pictures. All right, so we're going to start looking at the Z transform, because that's really that will set up some of the notations that will be useful after for the wavelets, and as well because that will set up the frequency domain for us. Okay, so we'll be able to look at the frequency domain. Right, so the handouts are on GitHub, but I'm just going to write down by hand a bit of what's going on. I'll try to go as slowly as I can, so everybody's on board. If there is any issue, okay, if something is not very clear, or if I make a mistake, please interrupt me and I can slow down, okay? Right, so we're going to look at the Z transform, and we're going to look at it in 2D, okay? Right, so just a recall of what we have, okay? So if we have three domains, if you want, of interest, okay? So one is the continuous domain. And in the continuous domain, try to zoom in a bit. All right, in the continuous domain, the signal we have, so we're going to look at it in 2D, okay, first. I'm sorry, in 1D. And I'm going to denote the signal as being x of some variable t, and t would be, I guess, the time here, okay? So then we had the discrete domain, still in 1D, where this time we said that the signal is sampled at some locations, and I would call that particular value x of square brackets of h, and h would be the index in your signal. And now what we'll be looking at is in the Z transform, domain, still in 1D, will be something called x of z, and v is a complex variable, okay? So that's a complex number. All right, so in 1D, the Z transform of your signal, so we won't be working with the continuous domain, we'll be only working between the discrete and the Z transform. So the Z transform of my signal is the sum from minus infinity of my samples. And here I have a power of my complex number. Sorry, it's h. Right? All right, so I do sum from minus infinity to plus infinity of, it's not h, not n, it's h. Okay, so of my integer h, so h is the index of where you are in the position in your signal. And you just say, well, my signal, instead of manipulating that as a sequence of number, I'm going to say now it's a polynomial, okay? And it's a polynomial of, so you have powers of z, and so you have z to the power of, so a whole bunch of terms, and so x of z now is a polynomial, okay? So it's a polynomial of complex, so it's a rather tricky thing to represent, okay? So to imagine, but just bear in mind, okay, this is just a mathematical construct that will allow you to do things in a more simple way when using convolution. Right, so we're going to look now at what's going on in 2D. Right, so in 2D, let's say you have, all right, so the continuous version. If you want the continuous picture, it's a real picture, that the one with the photons and so on. That would be, let's call it g of xy, okay? And xy would be the coordinates. Now, actually, sorry about that. I'm going to try to stick to MATLAB notations, okay? And you'll see why later. I quit y and x, okay? So we'll just start with the first dimension as being y, okay? Just the vertical, the vertical axis, and little x would be, small x would be the horizontal coordinates. In discrete, your discrete picture, that's actually the one you have access to. And that would be something like that. So hk. So h would be the vertical index, and k is your horizontal index. All right, and the z transform in 2D of that would be something like, so you usually capitalize the letter, so that would be z or g of z1 and z2. Okay. Now the names here, index, yx, hk, z1, z2 is just me for this handout. That's the way I've decided. I don't think there is a strong convention on that. It's just the way it is here. Okay. And so you can simply extend a definition of the z transform in 1D into something in 2D. And this is what it looks like. So you have the z transform of your two coordinates. It's a summation from h from minus infinity to plus infinity. And now you have a double summation because you have two coordinates of your pixel intensity and that particular coordinate. And then you have the monomials in z1 and z2. Okay, so I'm just going to say that. So basically, once again, so the z transform, you transform your 2D sequence, so your picture, into a polynomial in a polynomial of complex numbers. As I said, it's a bit complex to really understand what's going on here, or to have a mental representation of it. And that's because basically now it's even more complex than just for the 1D case, because 1D case you only had one single complex number and that was kind of like a 2D entity, okay, so 2 dimensions, so the real and the imaginary parts. But now you have 2 of those, so actually it's a 4D plane, okay, so you have 4 dimensions, and now you have to think of that as being a 4-dimensional polynomial, because you have, 2 real parts and 2 imaginary parts. So it's not trivial to visualize, but what only matters is what we do with that Z transform and why we have it in the first place. So let's see. Let's see how it works. Okay, so we are going to I'm going to give you some examples here, 2 examples, and how you construct it from your picture. Okay, so let's imagine that. So example 1. So G is defined. So I'm going to use again MATLAB notations, and I'm going to say it's a matrix defined by these 4 points. Okay, so that's your 4 pixels, and that's basically a tiny picture. Okay. All right. So what is the Z transform of that picture? So first we need to assign what the, because I have indices here, I have index h and k, so I need to somehow sort out where the 0, 0 coordinate is and how, how I go about indexing that. So by convention here, and it's just using MATLAB convention, the top one here would be coordinate 0, 0. Then this one would be coordinate 0, 1. And this one would be 1, 0. And this one, 1, 1. Okay? So it's just me setting up this, this convention. Okay? So just trying to stick to whatever you've seen in MATLAB. So you say that in this picture, the coordinate of the top left pixel is coordinate 0, 0, and then you move on down and say 1, 0, 1, 1, and so on. Okay, so the first coordinate here corresponds to the y, and the second one corresponds to the x. Okay. All right, so let's see how that applies to our okay. So so all we're going to do is to sum these polynomials, okay, and the coefficients will be given by basically the pixel values I have in that matrix. So let's start with this one. So you have 1 times z to the power of minus the coordinates, that's minus 0, and times z2 to the power of minus the coordinates, that's 0. Then I move on to this one. I say it's plus 2 times, and let's look at the coordinates. So that would be v1 to, so the y the first coordinate, so for z1 is still 0. And then you have the second coordinate, which is 1. So because we do minus here, okay, so remember it's minus, you have minus 1 here. All right, and then you can move on to this one, so plus 3 times d1 of, this time the h is 1, so that would be minus 1. And z2 would be minus 0. And then we move on to the next one, which is minus 1 for both. All right, so it's quite simple. So, I mean, the formula here looks a bit kind of nasty, but really what's going on is just you're going to look at the coordinates every time in your picture, and what you do, you extract the value of the pixel, you put that as a coefficient, and then here you have a polynomial with different, you have different factors, and the power of this factor is just minus the position in your in your picture. So basically, okay, if you look at the discrete domain, you have something that maybe looks like this. You have a particular coordinate is equal to some number, okay, so let's call it A. And then that in the Z transform, okay, you will transform that into something like A of Z1 minus H and Z2 minus K. All right, so if you have a particular value in your sample, which is given by the value is whatever, A, then that gets transformed into this little monomial of A times these powers of Z. All right? Okay, so that's kind of how you do it. It's kind of, there's nothing really tricky about that. The thing you have to be careful of is setting up your, when you have your picture and so on, like to set up properly to say, to know beforehand what is 0, 0 and how you index your picture. But once you've indexed your picture, when you know what the value of a particular pixel is, given its indices, then it's no problem. You can get the Z transform. Is that okay? Have I lost anybody? Right. Okay, so we'll do another example here. Are you okay with writing down that guy? Yeah. Sorry. Okay, so this time we're going to look at something non-causal. So we're going to assume that the picture looks like so. And this time, I'm just going to highlight this one. This number in red would be the center of your picture. And so we're going to assume that this is coordinate 0, 0. This will be coordinate 1, 1. This will be coordinate -1, -1. Okay, and this one will be 0, 1, and this one will be no, sorry, 0, -1, yes. And this one, no, it's not 0, -1, it's 1, sorry, minus, right. This one is -1, 1, and this one is 1, -1. Now this will be typically, for instance, your the mask of a convolution filter. Okay, so you try to look here at what what the convolution filter will look like when Z transforms. So here I take a 3x3 matrix and centered in the middle, and assume that will be the weights that you'll be applying for your convolution. And so what will be the Z transform for that? And basically, the way you go forward is the same. So you start with, so you have two complex values, numbers, so Z1, Z2 for your two coordinates. And I'm just going to go line by line. So I'm going to start with this one. I say it's, so this, for this one, is 1 times D1 of, all right, so because the coordinate is -1, and if you look back at the expression I wrote down before, the exponent is minus, okay, so you have something Z1 to the power of minus your index, okay? So here, because the index is -1, the power is minus to -1, so that would be 1, okay? And same for Z2 will be 1. And then I have 2 times, so Z1 will be still -1, So there'll be 1. But this time Z2 would be 0, so I'll leave that to unchanged. Well, I could write it here. And then we have plus 3 times D1 of 1, so that doesn't change, and to Z2 of minus 1. All right, so if you look at the first, if you look at the powers of Z1, because I'm traversing this first line, the coordinates stay the same and still going to be a power of 1. And then I can go forward, you know, I can say, I can complete the matrix quite quickly. Sorry. And so on and so forth. So D1 minus 1, D2 to the power of 0, plus 9 times Z1 to the power of minus 1. Sorry, why the... All right. Yeah, because the definition of the Z transform takes the power of minus the coordinate. Okay, something to be careful of. Okay. This is, by the way, similar to what you have in the Fourier transform and so on. You always have a minus, or in the convolution, definition of the convolution, you have a minus. Definition of the Fourier transform, you have a minus, and here you have a minus, and it's all for, I mean, they're all the same. Right? They all go for minus because the idea you'll see after is that all these things are related. Okay, so this is a bit cumbersome, but just, you know, try that. That'll be in the handouts, just, you know, as an exercise at home, just, you know, before the exam, kind of do 1 or 2 of those by hand, so you're sure you kind of know what's going on. All right, so why do we do that? Well, we do this transform mainly because of the convolution and, you know, to see how to study the linear systems, right? So the main thing is, what I'm saying is that if you have your system, okay, that goes from x of hk to y of hk, okay, so you have a linear system that will have that as an input and output that is your output, okay. Then obviously what will happen is that in the Z transform, all that would be very nice. You would have something like that. Okay, so you just have a simple multiplication of your polynomial. All right, so in your discrete domain, you have 2 pictures. And so one is, you know, the result of a linear system, so your convolution. And in the Z transform, what happens is that you have this polynomial and, sorry, right. So the output polynomial is just a multiplication of your input polynomial with the transfer function of your system, right? And the transfer function, of course, will just be simply the Z transform of your mask. Okay, so if you're doing your convolution and you have your mask, then this is just the same stuff. Okay, and remember this is the whole point. Like you say, all the kind of operations you have in the convolution are these, you know, sums and involve different terms. But really, you can express that. It's equivalent, like, you know, when you do multiplication of polynomials. Okay, when you have two polynomials, you multiply to each other. the kind of distribution you do between the terms is very much the same that you do for convolution. So the idea is to say, well, if we, instead of doing this convolution, treat this convolution thing as something complicated, we just say it's just a multiplication of polynomial. Okay, so the working in polynomial worlds allows you to treat convolution as a multiplication. All right, it's kind of the trick. Okay, so say that again. These two guys are polynomials, and when you do the multiplication of the two polynomials, what you end up with is the exact expression from the convolution. All right, the same kind of distribution of your terms is the same. So let's see that. So I'm not going to go. I'm not going to write it 100%, but this is in the slides. So you have. So let's look at a finite impulse response system, and so let's see what do the inverse z. What happened there? All right. I've lost something. Try connecting again. All right. Right. Okay, so let's try to do the inverse operation here. Okay, so so this is the z transform, and let's look at what the mass looks like. So let's look at the coordinates z1 0, z1 0 2. Okay, so I'll have so I know here for a fact that this is that will require a 3x3 mask. And I'm going to do the same. Okay, I'm going to look at, assume that the central coordinate is 0, 0. And then I'm going to say here that's -1, -1, 1, 1. And that would be -1, 1. And it would be 1, -1. Okay. So if you look at the term in a power of 0, 0, that's your constant. Okay, and that's 4. All right. So I know I have here a 4. So I'm just identifying all the terms of my polynomial, and I'm just going to replace those. Okay. So the constant term that doesn't have any z's, that's your z power of 0 and z2 power of 0. So that's your central point. That's 4. Then I have this term here, which is a power of -1 in Z1. So that means that we're looking 1 pixel ahead. And that means that you're looking at this pixel here. Okay, so that pixel here is Z1 -1. All right. So remember, everything is kind of opposite sign, all right? So if you want, in that direction, you have Z1, and that would be -1, 0, 1. So Z1 to the -1, that corresponds to this value here. So it's -h, remember? So Z1 -1, that would be this guy. And same here, if you have Z2 here, you have -1, Z2 plus 1, Z2 0, Z2 minus 1. All right? It's a bit confusing. Just get used to it. So I'm just going to fill in all the values I have, okay? So we have 4, that's fine. So this one, I say that corresponds to Z2 0 and to Z1 minus 1. So that's this guy, so that's minus 1. And then I have Z1. So Z1 is the opposite direction. So there'll be this one will be just Z1, and that's minus 1. And then we have something similar with Z2, and basically you have that. And nothing is defined on this point, so they are zeros. Okay, so we come back to the definition of a mask we've seen before, and this mask basically allows you to find edges in a picture because it compares the average of the pixels around you against the current value, and basically there is this is non-zero only when you have some texture or some edge or something like that. All right? No, I understand all that is confusing because all the indices got negative values instead of being the positive stuff and so on. But that's fine. Right, so if you have so this is what's happening, okay? So you have your system, and you know this is the output in the Z transform, and you do a multiplication of your input Z transform times the Z transform of your transfer function. And if you just do simple arithmetic on your polynomial, okay, so you algebra on your polynomial in complex polynomial. So here there's no mystery, okay, it's just like you plug in the polynomial and just do the algebra as you used to. What you get is something like that. And again, you can identify, okay, so you can do the transform, the inverse transform, by just observing that, okay, if you have xz1, z2, that really corresponds to the original signal sample. But here, if you have that, okay, so this is confusing. If you have a z1 to the power of minus 1, what you're looking at here is a shift in the x direction, and really you're looking at this guy here. Okay, so the h plus 1 basically will get transformed into z minus 1 to the power of minus 1 of your input signal, I think. Right? And you can keep on identifying all these guys. Okay, so the Z transform here allows you to come back to an expression where you do the inverse Z transform. Basically, you come back to the original definition you would have in discrete domain of your convolution. All right. And as I said, like the whole trick here is like the kind of operations you do for convolution really is similar to what you do for polynomial multiplication and identifying the terms of your polynomials, the coefficients. All right, so this is what you do when you do a FR filter. So it's quite simple. You just multiply both, and you find the solution. And it's a finite impulse response because basically the output here only requires a finite number of your inputs. And so basically, if your input is short-lived, okay, if you just have an impulse, okay, if your input is x is 1 and then x is 0 everywhere else, okay, so you kind of have in 1D, okay, so temporal signal, you you send something and then you stop sending the signal, so you have zeros everywhere. Then the output will stop to be 0 at some point as well. Okay, so the response of that short impulse will stop at some point, and that's why it's called finite impulse response. Okay. All right. So that last piece, which is a bit more tricky. Okay. Okay. Actually, that's an example. Sorry. And I'm not going to do it because it's quite painful to do, but it's in the slides. So we come back, okay? So we have here this input signal, and this is really just your tiny picture 1, 2, 3, 4, as I've described before. So similarly, okay, so you could, the exercise would be, I have this, one possible exercise at the exam would be, for instance, I give you the input image as the defined like this, just at the grayscale values. I give the mask of the convolution, and I say, right, go to the Z transform and do the multiplication there, and then come back to the digital world and give us the result of the convolution you had. Right? So that's a possible exam question. So anyway, so you have this small picture, and that's a definition when you apply the Z transform, as we've done before. And if you use H as exactly we had, which is this definition, then really what you have is you just multiply H by this other polynomial, and you develop all that, and you have 1, 2, 3. Well, you have 20 terms or so to develop, and then when you refactor everything, that's the final expression you have, and that's in the Z domain. And obviously, you can do the inverse Z transform, and that allows you to identify what the power of each of these guys. So this guy would say like you in coordinate 2, 1 in your picture, for instance. Right? And so I don't know if you can see here, but that's the coordinate 0, 0. So in coordinate 0, 0, you can see you have -1 here. And you can identify this way and can reconstruct the picture. Right? And that is, by the way, exactly what you have if you do a convolution. Okay? So if you go into MATLAB, so if you look into MATLAB, right, and you do a convolution, so I just have my small picture, and the other one is this 3 by 3 convolution filter. All right, so that's my picture. So all right, so that's my picture, and that's the definition of my mask. All right, so that's 4 is the central coordinate, and so when you do that, sorry. You get back this matrix, okay? And remember, this is bigger than the original picture. To the original picture, if you want, is only the central part. All these numbers here are all the numbers that requires access to pixels in your picture. So because you have a 3 by 3 window, you extend by at least a pixel on each side your final picture. All right? So that's something to, in the next lab, to look at, what the definition, where you crop, and so on. But basically, once you have that definition, you can reuse that matrix, which we have here, and that gives you back. So you could go directly from that expression back into here by using the Z transform from here to here. All right? The final point is, I will stop here for finite response and so on. So the RF filters, they're more complex. I don't know how much you remember about the first year, but basically you have a fraction. Okay, so you have on top, you have two polynomials on a fraction, and so this would be an example of such a filter. Okay, so this one. So you have 1 over the one we've just defined. Okay, same expression, but except this time instead of being at the numerator, it's at the denominator. And the way you go about doing anything with that, okay, because like it's not a simple expression, you come back to the basics. Okay, you say, well, I know that y is x times h, and so that's what I get from that. And then you're like, okay, well, it's just algebra, so I could multiply this expression on both numerator and denominator, and basically you put you come back to something you can solve. So it'll be y times this expression, this polynomial times x, and then you can go back to the discrete world by doing the same trick we had, but this time what we shift is not the input but the output. Okay, so we have now a relationship between your input pixel and all the neighboring output pixels. Okay, so an input pixel has an impact on all the output pixels in the neighborhood. But then, of course, the problem here is like to compute these output pixels y, and similar to any infinite impulse response system, you depend to compute this guy. You need to compute all the other values that you have, neighboring values of y. Okay, so somehow you need to have computed y for all the other values before you can compute this particular output. All right, and that's the problem with infinite impulse response systems, is that you need to access to the future somehow. All right. Anyway, so that's a similar. All that is just an extension from what you've seen in with 1D signal. You can do the same with 2D signals. But the last point I wanted to make is kind of where it stops, because in 1D you've seen a lot of study on stability. Like, okay, you have a RF filter and you want to know how stable that is, and you'll be looking at the poles of your system and trying to identify them to see how far they are from the unit circle and so on. Here we don't have to do that because it's just simply too complicated. Okay, it's not because there's no issue there. Okay, there's plenty of issues. It's just like the theoretical framework is just way too hard. Okay, so just to give you an example, to look at to look at the zeros of a polynomial, basically now you're looking at a surface in a 4D complex space. Okay, so if you want to find membranes in spaces, in complex spaces, be my guest, work on it. I'm not going to cover that. Okay, so basically, good news for you is it's just too damn complicated, so we don't even bother. All right. So that would be it for now, and right, so see you tomorrow for the lab.